Hello guys, this is Paul McWhorter with TopTechBoy.com, and we are here today with lesson number 8 in our incredible new tutorial series where you're going to teach those robots who's boss. I'm going to need you to pour yourself a nice big mug of iced coffee. That would be strong black coffee poured over ice, no sugar, no sweeteners, none needed. I'm also going to need you to get out your Elegoo Smart Car 3.0. What? You don't have your gear yet? Look in the description down below. There's a link over to Amazon and you can pick up a kit for yourself and you can play along at home. Hey, as always, I want to give a shout out to you guys who are helping me out over at Patreon. It is your encouragement and your support that keeps this great content coming. You guys that are not helping out yet, think about looking down in the description. There is a link over to my Patreon account. Think about skedaddling on over there and hooking a brother up. But enough of this shameless self-promotion. Let's jump in and let's talk about what we are going to learn today. And I do believe, if I remember correctly, and I do usually remember correctly, you had a homework assignment from last week. And what that homework assignment was that in lesson number 7, we had done a calibration of the car where we could calculate how far it would go, and then we could give it a desired target distance, and it would calculate how long the motor should be on, and it would drive for that long, and it would go that distance. Worked great. Then we also kept that working and put in an ability to control the speed, but we sort of put the speed in by giving the parameter that we write to the motors. And so if we wrote 255, that would be full speed, and if we wrote 100, that would be kind of the smallest write value that we could use where the car would still move reliably. And so really we were working with a parameter of write value, which is what the Arduino wants, to where in the real world we think more in terms of velocity. And so what your assignment was for this week was to be able to set the desired velocity, like I want to go 2.25 feet per second, something like that. I think, what did we say for last time? It was like 2.26 feet per second was the fastest that the car could go if we wrote 255. That rather than specify the right value, specify the actual velocity and have it move at that velocity but still go the right distance. So you were to be able to specify the velocity and the desired distance. It would go that speed and it would go that distance. Okay, how many of you guys were successful? Actually, this was kind of an easy homework, and I hope you guys saw this as an easy homework, because really it should have been easy, because the hard work was done. The hard work was done last week in coming up with this equation, right? It was this equation that was kind of hard. But really, if you look at that, this equation has velocity and it has right value. But it's just the problem is we're picking a right value and then calculating the velocity. And that's kind of backwards. What you want to do is you want to let the person pick the velocity, and then you calculate the right value. Well, the good news is we don't have to go in and completely come up with a new line. All the calibration is built into this equation, but we just need to rewrite this equation. So I am going to come over here, and I think the best thing would be to do it over here, because if I do it over here, then we will be able to see it when we go to our code view. So I'm going to just see if I can kind of erase some of this, and then we'll start up here and start doing our math. So let's start just by writing the equation as it exists now. And that is V, and I didn't want to use that color. That is V for velocity is equal to 0.0075 times the right value plus 0.35. Now, if we want to rewrite this equation, what we want to do is we want to get right value, WV, by itself. Well, why is WV not by itself? Because of the 0.35. We want to get rid of the 0.35. Can I just not write it? No, but how do I get rid of it? Well, you got to remember, Algebra 1, whatever you do to one side of the equation, you do to the other. And what's the easiest way to get rid of the 0.35 would be to subtract it. But if I subtract it from the right side of the equation, I've got to subtract it from the left side of the equation. So let's go ahead and do that. And so I'm going to have V minus 0.35 is equal to 0.0075 times the right value, and then plus the 0.35, because that's what we had before, and then minus the 0.35, because if I subtract it here, I have to subtract it here. So I haven't changed the equation, I've just reordered it in a nicer way. So then what does that give us? It gives us V is equal to 0.0075 times the right value. All right, in 0.35 minus 0.35, it becomes 0. All right, now WV is a lot closer. Ooh, and I forgot, I made a mistake there. I hope you guys were screaming at me. I got to leave the V minus 0.35 over here. V minus 0.35, okay, because it stays on that side. And now, why is WV not by itself? Because of the 0.0075. Well, because 0.0075 is multiplied by something, you can't subtract it off, but what you can do is you can divide it out. So we're going to take, and make sure, guys, to use your parentheses, because we want to divide this whole side of the equation, V minus 0.35. We want to divide the whole side of the equation by 0.0075 is going to be equal to 0.0075 times the right value divided by 0.0075. So I'm still following those rules of algebra. Whatever you do to one side, you do to the other. I divided both sides by 0.0075. Okay, so now we're going to have V minus 0.35 over 0.0075, and the 0.0075s cancel, right? No! No, no, there's no such thing as canceling. There's no such thing as canceling. Why do I say that? Because if I teach you to just mark out this and mark out that, like if I teach you, like you probably do, to do that, that is wrong. And while in this case it gives you the right answer, if you think of things that way, then what you're going to do, you're going to come along and you're going to say A plus B divided by A, and you're going to say, oh, the A's cancel. And that's wrong. Just because something in the numerator and denominator, you can't multiply it out. Think of, let's say, A is equal to 3 and B is equal to 2. Well, if I have A plus B over A, that would be 3 plus 2 over 3, which is equal to 5/3. And that is the correct answer. But let's see what happens if we use the cancel technique. A plus B over A, we cancel the A's and we're left with B. Then we would say that it's equal to 2. And that's clearly the wrong answer. So I can tell you as a math teacher that one of the biggest reasons that people do poorly in math is they do these things that aren't math, like canceling. But I have digressed enough. Let me get back to this lesson at hand. And what we're going to do is we're going to come in and say this is equal to, well, what can I do? Well, I can kind of rewrite it like this. I can pull those 0.0075s out and say it's 0.0075 times the right value over, I did not mean to do that. Let me erase that. You pull the 0.007s out together like this. So you say it's 0.0075 divided by 0.0075, and then times your right value like that. Now, the 0.0075s don't cancel out, but they do make 1. A over A makes 1. 0.7 over 0.7 makes 1. 0.0075 over 0.0075 makes 1. And so you don't have to, when you end up with a 1, you don't have to write it. So we're going to end up with V minus 0.35 0.035, and I need to use my parentheses, over 0.0075 is equal to right value. And now let's rearrange it where the right value is on the left, so we can say right value is equal to V minus 0.35 over 0.0075. And this is the equation that we need, that now the user can specify a desired velocity and then calculate the needed right voltage. And so that is kind of neat, and I will get further out of your way because I know how angry you get when I cover up what I'm writing on. All right. Now let me also just show you another quick math tip, why you always want to use your parentheses. So notice two things. I always use my parentheses, and I use a horizontal line for divide. Because like if I have, let's just say that I have x is equal to 2y plus 4. No, that's not a good one. That's not a good one. Let's say that I have x minus 4 is equal to 6x. Okay, and let's say now I'm going to divide both sides by 6. Well, I would say x minus 4 divided by 6 is equal to x. Now, what is wrong with this? This looks like x minus 4 over 6, and you're only dividing the 4, where really you have to divide the whole side of the equation. So if you use your parentheses, it becomes very clear that not just the 4, but the x is divided by the 6. But it makes it even better. It makes it even better and less ambiguous if you use a horizontal line for divide. Because if I say x minus 4 with parentheses divided by 6 is equal to x, this is very clear what you're talking about. Okay, just again, another little tip of grading math homework and seeing people end up getting in trouble because they don't use parentheses and they use a slash for divide instead of a horizontal line. Okay, but I digress. Let's get back to this, and I think what we can do now is we can call up our Arduino code. And just a recap, what are we trying to do? Now you get to pick the velocity that you want, and the velocities we saw last week, at least for mine, I could go at the low end of 1.1 feet per second and at the high end 2.26 feet per second. So I can pick a velocity between those two, and then I will calculate a right value, and then if I put that right value into the smart car, I will get the velocity that I wanted. Okay, so let's call up a fresh new Arduino IDE, and I think what we will want to do here is, that is kind of strange. Did that look strange to you too? Okay, there, much better, much better. All right, so now let's start where we left off last week. So let's go to the most excellent www.toptechboy.com, and you can use the happy little green search icon, and you can search on Robotics Training Lesson 7. You'll be brought to this page, and then down here we have our code. You can come in and you can select the two little pages, right mouse click and copy, and now we can come back over here, make sure it's empty, right mouse click and paste, and we are where we left off last week. And remember, we had this forward function, backward function, left turn and right turn functions, and then where we kind of ended up was that we could select a right value, 255. We know that that would be full speed, and then we could set that speed, and then we could just say the distance that we wanted to go, and it would go that distance. All right, but we're not going to do that. Now what we're going to do is we're going to specify a I think I can come back up here now. We are going to specify a velocity that we want, and then we are going to calculate the right value. And so if we're going to specify a velocity, if we're going to calculate a velocity, we better come up here and declare it. And so I'm going to come up here, and velocity will be a float because, right, we might have 1.1 feet per second. So we're going to say float is our velocity. And then we're going to come here, and then we are going to just set a velocity. Let's just set v is equal to 1.1 feet per second. And now we are going to calculate the right value. And the right value is going to be, I guess I should get out of your way so you'll see there. Right value is going to be, with parentheses, v minus 0.35, close parentheses. What is going on here? What is this nonsense? Why did that not work? Okay, right value is going to be v, the velocity, minus 0.35, close parentheses, divided by 0.0075. All right, and we will put our semicolon in, and we will put our semicolon in, and we'll get rid of that white space. Okay, so that will calculate right value. Now the left motor will set to the right value, and the right motor will set to right value. We're not doing this now, but we're just keeping left and right separate in case we want to play with that in the future. Then we set speed. Okay, we set the speed with right value, but the only difference is this time we didn't just specify right value, we calculated right value based on our desired velocity. Does that make sense? And then we just said, okay, go forward by 4. Okay, go forward by 4 feet, and then we passed right value down to our function. Well, now we don't pass right value, right? We pass velocity. Or no, we can pass right value. Yeah, we'll pass it the right value because we just calculated it up there. We'll pass the right value. And then let's go down to forward, and it's going to grab the right value. Okay, it's going to grab the right value, and it's going to grab the distance. And then what it's going to do is it is going to calculate the velocity, but it doesn't know that equation. So no, what we are going to do is we are going to pass it. What do we want to pass it? It's just there's several different ways we could do this. And so let's think what would be the best way to do this. We should pass it the velocity. Okay, we should pass it the velocity because that is what we care about. So we know the velocity that we want, and then we're going to go forward at that velocity. And we know that velocity is right because we already set it here, but we just got to let we've got to let that function know what velocity we are operating at. So we will come down to forward, and we will bring down velocity. And since we are floating velocity here, we don't have to declare it here. So we will take this out. And now we're not calculating velocity down here because we already did that. We're just passing it velocity. But we still have to calculate t. Okay, because you remember distance is rate times time, or distance is velocity times time. And so time is distance divided by velocity. And this times 1,000 is just because we are operating in our mind in seconds, and Arduino wants milliseconds. So to convert seconds to milliseconds, we multiply by 1,000, and then we delay that long. And that should work. Let's go ahead and fix backwards while we're at it. We'll pass it v. And then we don't need to float v. We don't need to calculate v because we already know it. And now we need to come up here, and if we call it, we need to make sure to pass it velocity when we call it. But we're not calling it. What the heck? Why don't we call it? Let's say backward, and let's go 4, velocity. And I think that that should work. Okay, so I'm hoping this makes sense to you guys. Let me get this plugged in. And let's see if I can go to a little better view for you so you can see what I'm doing. Okay, so I will be plugging this in. I really think this is going to work. That is unfortunate that I've left the car on all this time, but that's okay. Let's turn this thing to download. Look at that. Look at that, guys. I am smoking today. Can you see that? I am smoking hot because I did that program without making a mistake. I do need to adjust my window size a tiny skosh there to make sure you're seeing everything that I'm doing. Okay, the program is downloaded, and I think we said to go at a velocity. What velocity did we set? We set a velocity of 1.1, so that should be slow, and it should go forward 4 feet and backwards 4 feet. So let's go try that. I need to take you over to the most excellent RoboCam. Okay, let's go and let's take a look here. We are going to set this on the starting line. Okay, we're going to set it. I'll let it run one time and then I'll hit the reset. Okay. Now I will hit reset. It's on the starting line. Ready, set, go. And it goes 1, 2, 3, 4. 1, 2, 3, 4. Oh man, did you guys see it? It nailed it to the inch. To the inch. That thing really worked well. Did your guys' work as good as that? Okay, let's say we are going to go. We are going to go at a higher speed. And I believe the high speed that we said that we could go at, was 2.26. So let's go full speed. So the velocity is going to be 2.26. Okay. And then let's go forward 10. And then let's go backwards 10. Okay, forward 10 and backwards 10. So let's go ahead and download that. So we'll come over here now and send that down. Okay. I like letting it run the first time. Okay. And then remember, the reason it's not looping is we put this little trap so it'll run one time and then stop. But it should go 10 feet forward, full speed, 10 feet back. Okay, so let me give you the RoboCam view. And we have it set to 10 feet forward, 10 feet backwards at full speed. So let's see what happens. Okay, we are on the starting line. And ready, set, go. And we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, man. Do you guys see this? It nailed it. Why? Because we did the math. We did the math, and it absolutely nailed it. It is like maybe a half inch off. Maybe a half inch off. That is like really good. I am pumped up about this. And the reason I'm pumped up is because math works. You try to do this by trial and error and see how far you get. Okay, let's try a different one. Let's try, what if we go 8 feet? So what I'm going to do, whoa, that's why I'm always holding it so it doesn't drive off the edge. So let's say that we're going to go 8 feet forward, okay, and then let's reset the velocity. So I'm going to get this code. I'm going to copy it. So I'm going to go 8 feet forward, and then I'm going to reset the velocity. Ooh, let me give you a code view where you can see what I'm doing. Okay, let me undo a couple of those things. edit, undo, edit, undo. Okay, so what I'm going to do is I'm going to grab this code where I set the velocity, and I'm going to copy it. And then after I go forward, I'm going to come back here. Okay, so I'm going to go 8 feet forward at a speed of 2.26. And then after I go the 8 feet forward, then I'm going to want to go slow at 1.1. Okay, 1.1. Okay, and then I'm going to recalculate the right value because I changed the velocity. Now I have a new right value. I set it for the left and I set it for the right. And now I'm going to set the speed again, and now I'm going to come backwards the 8. So what is this going to do? It's going to go forward fast 10 feet and then 10 feet backwards, but only slow. But it should still, if the math is kind of good, it should still get back to the same starting point, even though it comes back a lot slower than it went. Okay, so let's download this. Let's make sure that we switch over to RoboCam. And now we're going to go out there and we're going to see 10 fast forward, 10 slow backwards. All right, guys. Here we go. Here we go. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, it came back. It missed it by about 6 inches on the way back, and so on the way back the calibration wasn't perfect, but a 6-inch error out of 8 feet, that's still like within 10%, so that is still good, and I'm still happy with that result. Okay, I'm still happy with that result. And let's try one more. Let's try an intermediate one. And so let's see, let's come over here and let's say that what if we go forward at, let's go forward at 1.5. That's kind of a middle range. And then let's go the 8 feet. And then let's come back 1.5. velocity, 1.5 feet per second, and then let's come back to 8 feet. So let's see if it's still working kind of at an intermediate value. So I'll plug this thing in and download it. Here we go. And you guys, I had the wrong view and you didn't see the car. There it is. Okay, that seems to be working. So we're going to want to see 8 feet forward and then 8 feet back. So we will come back to RoboCam. We will come over here. We want to see 8 feet forward, 8 feet back at sort of an intermediate speed. Okay? So this is going to be 1, 2, 3, 4, 5, 6, 7, 8. It went like 9. Okay. It came back and it nailed it as far as it ended up back where it started, and that's good. But it went more like 8.5 feet. And so again, what that is meaning is that it works perfectly at the endpoints. Where is my cursor? It's working perfectly at the endpoints. And so remember, we had 2 data points that we used when we calculated this graph. And let me give you the graph view. Okay, we had, let me erase this. If I make my eraser bigger, then when I just make a small mistake, it's kind of hard to erase. But let me get this. Okay, so what we know is that we calibrated it for a right value of 100 and a right value of 255. So we know that those two values are correct because we calibrated at those two values. But then we made an assumption. We assumed that between those two that everything was linear. All right. Now, why do we assume that? Because then we only have to do two calibrations. But what we see is at this midpoint, it really seems to be going faster than what we had thought. And so it seems like that our curve is not really a line, but is a little bit more of a curve like this, okay? And so the further that we get away from those 2 points that we calibrated at, then this is our error, okay? And it looked like at 8 feet, I was about, let's say 0.8 feet off. And so again, our accuracy is still within about 10%. But it's not as good as at the points that we calibrated at. Well, if we wanted to do better, what could we do? We could calibrate at more points, and then we could kind of fit a line for these different segments, and then we could choose the calculation. We could have a different line for each one of those, and then we could use the equation for that particular line. But for something like this, what I'm going to say is I'm going to say that for my application, 10% is good enough. And so let's kind of just pause and think about what we've learned here and think about some of the things that we have figured out. What is something that I really like? Well, first of all, I like that math works. And by simply doing the math, we're able to get this thing to do really, really, really well. We can tell it how fast to go, it goes that fast. We can tell it how far to go, it goes that far. And it's keeping the calibration really, really well. Now, what are some reasons that it's not working perfectly? Well, one reason that it's not working perfectly is we made a reasonable assumption of linearity. We made a reasonable assumption of linearity in the velocity versus right value curve, and in fact it's probably not perfectly linear. And so that assumption made it easier to calibrate but cost us a little bit in accuracy. The other thing that I seem to be noticing is let me start again here, that like yesterday I'd kind of been working on this thing all day, and then after working on it all day, I calibrated, okay? I calibrated it. And I calibrated it to those two measured data points. But at this time, the batteries were kind of like running down a little bit. I mean, it was still plenty to make it go, but the batteries were not fully charged. And so these data points were probably a little bit low because the battery was low. Then this morning when I came in and I charged it up overnight, I was getting what looked like it was running faster than what it was yesterday. So I was getting something more like this. Well, then I play around with it this morning, and then I come to make the video, and the batteries had time to discharge a little bit. And by the time I made the video, it was kind of like I was right back on top of that calibration curve from yesterday. But what you can kind of see is there's going to be a error that is introduced because the actual calibration depends on the battery charge. Okay, so let's just kind of talk about errors here. Again, we want to think like engineers. So I'm going to erase some of this work here. I'm going to think like an engineer, and I need to let you see what I'm working on. So I'll come over here. And so let's talk about sources of error. The first one is the battery state. For a given right voltage, a hot battery will make the car run faster. And so depending on if you calibrate on a hot battery or a running down battery, you're going to get a slight difference, and that's going to be this curve moving up and down, and that's going to be an error. Okay, that's number one. Number two is assuming linearity. Assume linearity. When I assumed that it was a straight line from here to here, okay, it's really not a straight line, it's really more of a curve, and therefore as I get in these middle regions I have an error because of my assumption of linearity. I can kind of live with that. There is a third error that I'm seeing, and remember at first we kind of done the turning business, okay, and then we haven't played with turning, but we got to come back to the turning. What I am finding is I am finding that the turn is a little hard to calibrate, because what tends to happen when you start up, if let's say these motors started a little bit quicker and let's say it slipped a little bit, if the motors slip when you start the motors up, if the tires slip when you start the motor up quickly, it can lead to a little this kind of thing. And now instead of going straight down the track, you're starting with an error because the motors kind of made the tires slip a little bit. I'm wondering if maybe if we tried to kind of ramp the speed up a little bit, maybe it would make it a little bit easier to do that. Also, it seems like sometimes when I just run the thing, there's a tendency for my car to veer to the left. And let me just see if I can sort of show you. And again, you know, this is a very affordable platform, and then that means that things don't work absolutely perfectly. And so I'm trying to get this where you can see it. If you watch the tires as this thing goes, do you see how, let's see, it's this one has a little bit of wobble in it. If you look at this one, it's kind of going like this a little bit. It's wobbling. And the others don't seem to do that, but that one motor just seems to be in there. The tire is mounted a little bit off axis. So if you have three tires that are going perfectly straight and the other one is wanting the car to go a little bit like this, that means the car might not go exactly perfectly straight. Okay, I have been impressed that I can go 10 feet and come back and I'm not like veering off track by a foot or so, but that's kind of a little bit of a cause of error too. And so this is this would be like tire slippage would be a cause of error. And then the fourth thing would be tire wobble. Okay, and let me put that up there where you can see it. So the four sources of error is the battery state. We're assuming linearity in the velocity, that we could have tires slip, that if if parts of the tires started a little bit quicker, it would go like this, or if they slipped, it would go like this. And then the final thing is that tire that's wobbling. And so those are probably, as far as I see, the four largest causes of error. But I think it's doing amazingly well. And then kind of like, again, the reason it's never going to be perfect, we want to be as careful as we can. We want to do the math perfectly, and we want to be as accurate as we can. But the reason it's never going to be perfect is we tell it where to go, but it doesn't really know where it is. And so if it had something to read or to know where it is, it could do like mid-course corrections to adjust as it's going and not just be operating completely open loop. And we'll probably play around in this lesson. That's something that maybe the ultrasonic sensor could help us with, or if you look on the bottom, that set of diodes that'll sort of read a reflected optical signal. And if we start incorporating some of those other things, we can start kind of improving the accuracy. But I want to show you is that you don't want to get your accuracy by depending on a control system. You want it to be as accurate as possible, open loop, and then you want to apply whatever control algorithm that you're going to use in order to try to drive out some of the errors. And we'll be talking about that in future lessons. But what your assignment is for next week, if we go back to our code view, remember that we've been working on forward and we've been working on backward, but as we've been monkeying around with these equations and playing with changing velocities and changing speeds, we have broken our turn left and turn right functions because they were just assuming full speed. And so that spinning was calculated based on full speed. And so there was sort of like something that would rotate you 90 degrees, but the function has built in an assumption that you're going full speed. And if you're not going full speed, then that calibration is going to be off. And so what your assignment is for next week is to get this thing fixed where you can now, still controlling the speed of the forward and backwards direction, fix the turn left and turn right where you can still specify a degree turn and it will make that degree turn. That's the homework for next week. Okay guys, I hope you are having as much fun taking these lessons as I am making them. I am just really having a lot of fun with this and really look forward to some exciting new lessons in the future. If you guys are enjoying this video, make sure to give it a thumbs up. If you haven't subscribed to the channel, make sure that you subscribe to the channel. Share this with other people. Post it on social media. Let's see if we can get a little sense of community built around this project. All right, guys, that is pretty much it for this week. This is Paul McWhorter with TopTechBoy.com. I will talk to you guys later.